So all chemical reactions do one of two things. They either release energy or they absorb energy. So a chemical system which releases heat into its surroundings is called an exothermic reaction. And so that word exo means on the outside. You know, like an exoskeleton is on the outside of something. And so the reason why is because the heat is flowing into the outside, into the surroundings. And so an exothermic reaction would cause its surroundings to heat up. And so if you touched a chemical system that was exothermic, then it would feel warmer. You would feel warmth coming off of that system. Now, a chemical system which absorbs heat from its surroundings, that the heat is flowing into the system, and therefore the system's energy is increasing, is called an endothermic reaction. And so if you were to feel an endothermic reaction, it would feel cool to the touch because it would make its surroundings cool, and you are one of its surroundings if you are touching it here. So exothermic reactions are releasing heat from the system, releasing energy from the system to the surroundings, and so therefore the system is losing energy and the surroundings is gaining energy. It's a heat flow out, and so an endothermic system, on the other hand, is one where heat flows into the system away from the surroundings. The surroundings then feel cooler to the touch because the heat is flowing out of the surroundings and into the system. And so in an endothermic reaction, the reaction is gaining energy. So most chemical reactions that we see occur are in Earth's atmosphere. You know, we do them in a lab. We don't do them in pressurized vessels. We don't do them on space or something like that. So most chemical reactions are in the Earth's atmosphere. And the Earth's atmosphere has a roughly constant pressure. It does change as the weather changes, but for the most part it stays about the same. It may change, you go up a mountain or something, but you know, most of the time if you're doing a reaction in a laboratory, that pressure is going to stay about the same here. Now, because of the fact the pressure stays the same, for most of these reactions, only a tiny amount of work is done by the system. And so that means for most reactions done on Earth is that our delta E that's equal to work plus Q is that the work is 0, which just turns this into delta E equals Q. And that's going to be true if we're at a constant pressure. So the change in internal energy at constant pressure is equal to Q, the heat flow in or out. And so for a constant pressure reaction, okay, one like we're talking about here, the heat absorbed in the reaction has a special name, and it's called the enthalpy change. And so this word enthalpy right here is the one we'll be focusing on a lot during this section here. It comes from a root word that means heat, but we're going to use the word enthalpy just to be precise with our terminology. And so logically, or somewhat maybe illogically, considering the fact that we said it sort of means heat, but we're using it to not use the word heat, is the symbol for enthalpy change is delta H. And so H is enthalpy, and so delta H is enthalpy change. And for constant pressure reactions, that heat absorbed, that Q, is equal to the enthalpy change. And so we can define our enthalpy change, delta H, as being the change in internal energy of a reaction at constant pressure, which is equal to the heat flow for that reaction. So let's look at our endothermic and exothermic reactions. For an endothermic reaction at constant pressure, the enthalpy change is always positive. And the reason why is because endothermic reactions absorb heat. Because they are taking heat away from their surroundings, so their surroundings cool down, so they gain heat, the heat flows into them, and so they will have a positive delta H, a positive enthalpy change, okay, because they will increase their total energy. On the other hand is that if you have an exothermic reaction, it's that constant pressure like we said, the enthalpy change is going to always be negative. So always negative enthalpy change for an exothermic reaction. And the reason why it's negative is because if it's exothermic, then it's heating up its surroundings. Heat is flowing out of the chemical system. And so if it's flowing out, it's releasing heat, then the system must be losing energy because it's giving it away to its surroundings as heat. And so therefore it's decreasing its total energy. And so that's sort of delta H here. So if you saw something that said delta H is equal to 30 kilojoules right here, you'd say, 30 is positive in this case. And if it's a positive value, then that means that it must be an endothermic reaction. If you said that delta H is equal to negative 107 kilojoules, then you would say, for this particular reaction, then it must be an exothermic reaction. So that we would know that if that reaction was going on, we touched it, it would feel hot. If we had this delta H, this plus 30 kilojoules here, then that would indicate that it would would feel cold because it would be an endothermic reaction. Now, moving forward, so we don't have to say every single time at constant pressure, we are going to assume that all reactions are at constant pressure, unless you're given information that would suggest otherwise. Now, as we said, all chemical reactions either release or absorb heat, and so they're either exothermic or endothermic. I guess technically it's possible to have a reaction that has an enthalpy change of 0, but they aren't very common. But since all chemical reactions either release or absorb heat, each particular chemical reaction has its own enthalpy change for basically a simplified balanced chemical reaction. And so that own enthalpy change for each, the specific one for any particular reaction, is called the standard enthalpy of reaction. And so the symbol that we're going to use for that is going to be delta H naught. It's sort of hard to see here, but it's a delta H, and it looks like a degree sign or a 0 that's up above it here. So the difference between delta H is just the enthalpy change, could be an amount for any particular system here, but if we're looking at one particular reaction, say something like H2 plus O2 yields H2O, and I guess that in this case we need to balance it, right? Because we have 2 oxygens here, only 1 here, so we put a 2 out front here, put a 2 out front there. So this particular reaction, 2H2 plus O2 yields 2H2O, has its own particular value for the standard enthalpy of reaction, delta H naught. So this would be what the standard enthalpy of reaction is. Now, a couple other terms you'll hear for this. Standard enthalpy of reaction is a little awkward to say over and over again, and so sometimes you'll hear it shortened to either enthalpy of reaction, dropping out the change even though it is a change. You'll sometimes hear it called the heat of reaction. Remember, we said that word enthalpy basically has a root that means heat, and sometimes it's called the standard enthalpy change. There are a couple other terms that are used, but you'll hear me use these various terms here. So sometimes I won't call it standard enthalpy of reaction. So if you hear enthalpy of reaction, heat of reaction, standard enthalpy change, know I'm talking about this delta H naught, meaning standard enthalpy of reaction. So this enthalpy change depends on the conditions of the reaction. So it depends on the temperature, it depends on the pressure, it depends on the concentration. Delta H naught is typically taken for certain standard conditions. Most commonly, it's 1 atmosphere of pressure, okay, 25 degrees Celsius, and if the substance is an aqueous solution, a concentration that's 1 molar. Most of the time, this isn't really going to apply, and if we have circumstances where we're close to this, so if we were at 1.05 atmospheres, or we were at, let's say, 35 degrees Celsius, then delta H naught is not going to change by much. It's going to be very close to the value that we have. But technically, to have the correct value for delta H naught, to have the correct value for that standard enthalpy of reaction, it needs to be at these conditions. And oftentimes what will happen is we'll sort of let the reaction happen. We'll start it at this system and then sort of let it return to it. And then we'll measure that heat as it goes through so we can use this delta H naught. But technically, it does need to be under those particular conditions. So let's look at an example. Let's try that reaction we just talked about, the combustion reaction of hydrogen to produce water. So 2H2, which is a gas, plus O2, which is a gas, yields 2H2O, which is in liquid form. We know it's going to be as H2 is a gas and oxygen is a gas in this case because we said that we're at 25 degrees Celsius for this situation. And so that means hydrogen would be a gas, oxygen would be a gas, and water would be a liquid. Now over on our right, you can see that we've listed our delta H naught right here, and so this is typically how it's written. Usually you'll write the reaction out on the left and then write that standard enthalpy change on the right. And so the units we have here are going to be kilojoules per mole, and we'll talk about that a little bit in terms of how exactly that works. But basically, it's an energy per mole of reaction is the term that we'll use. So in this case, let's take a look. So delta H is negative 43.6, and so that would indicate that if we started off with our reactants over here, 2H2 plus O2, is that the energy of the system would drop. And so if the energy drops, drops in the system, that meant that energy had to go somewhere because energy cannot be created or destroyed. It has to, in this case, because the fact that we said that it doesn't say anything about the pressure changing, so it's under constant pressure. No work done means this has to go away in the form of heat, and so this heat is being emitted by this reaction, and it's going to flow into its surroundings. So its surroundings are going to heat up, which makes it exothermic, which we could have answered much quicker just by saying, hey, delta H is negative, so therefore it must be exothermic. And so just as we see here, delta, since it's exothermic, delta H is negative. And the standard enthalpy change here is negative. Now, we also say this, since delta H is at standard conditions, note that each of the products and reactants are in the phase expected. We already talked about that. Gas for hydrogen, gas for oxygen, and liquid for water. So continuing to look at this reaction, the negative 43.6 kilojoules is the heat released by 1 mole of reaction. So we said it's kilojoules per mole. And so that mole, you ask, well, mole of what? Mole of reaction. New term here. So a mole of reaction, sometimes abbreviated as mole RXN. RXN is a common abbreviation in chemistry for reaction. But mole reaction is a shorthand notation to indicate that if 1 mole of a substance is reacted or produced, then delta H is the amount of heat absorbed or released for that situation. So in this case, we look at the coefficients. What this particular reaction indicates is we have 2 moles of hydrogen gas, 1 mole of oxygen gas, 2 moles of water vapor, or sorry, of water in this liquid water in this case. And so since delta H is 43.6 kilojoules per mole for this particular reaction, it would mean that if we were to use up 1 mole of O2, then this would produce, or this would give off 483.6 kilojoules of energy. Now, on the other hand, if we had 2 moles of oxygen that were produced here, 2 moles of oxygen would release twice that. It would do 43.6 times 2 would be the amount of energy in kilojoules released by this particular reaction here. So standard enthalpy is a reaction, always the amount of heat for the particular number of moles of reactants and products in the balanced chemical equation. So that's sort of how that works here. Now, what if we started off with this? I said, but I have 2 moles of H2 here. Well, what we'd have to do is that if you said, oh, I've got 2 moles of H2, we really are just going to have to do a conversion. So you're going to say I have 2 moles of H2 right here. If we set up our table, we'd say, okay, well, how many moles of H2 are there for every mole of reaction? Well, according to this coefficient, there are 2 H2s for every 1 reaction. And so what we do is we would say 2 moles H2 and 1 mole reaction. And then if we were trying to figure out the energy released by that, we'd then use our standard enthalpy change, our heat of reaction, to figure this out. And we'd say that 1 mole of reaction is going to go into negative 483.6 kilojoules because they're 43.6 kilojoules per mole of reaction. And then we could just use a standard conversion, sort of a unit conversion here, or a stoichiometry type problem, a mole conversion to basically work out what this is. And so this would be how you'd go about doing that conversion here. So this 43.6 kilojoules would be if you reacted 2 moles of hydrogen, 1 mole of oxygen, or 2 moles of, or produced 2 moles of water in here. So that's what we mean by mole of reaction. So we can use this standard mole conversion to convert from a number of moles or a number of grams of a substance, 2 moles of reaction, then finally to heat. And so let's look at this situation, a little more complex than the last one we saw. How much heat is released or absorbed by burning 14 grams of hydrogen gas in excess oxygen at 25 degrees Celsius? So what we want to do here is we have the amount of hydrogen gas, 14 grams. And so we're going to convert from grams of hydrogen gas to moles of hydrogen gas, then moles of hydrogen to moles of reaction, and then moles of reaction into our amount of energy by using our delta H naught. So we'll start off here just with 14 grams of H2. And so we're going to set this up here. So we're going to cancel grams of H2. We're going to go to moles of H2. And so in 1 mole of H2, you look on the periodic table, the molar mass of hydrogen H2 is 2.02. And so that's going to cancel grams H2. Now we have moles H2. Since we're trying to find this kilojoules per mole, we know that is moles of reaction up here. We're going to have to get rid of moles of hydrogen. We're going to go to moles of reaction right here. And we say, what's the mole ratio? Well, there are how many hydrogens? There are 2 hydrogens for every 1 mole reaction. The mole reaction is typically always going to have a 1 if you use a simplified balanced equation like the one that's right here. So that cancels out moles of H2. Now we have moles reaction. And so we want to get rid of moles reaction, and we want to go to use our enthalpy change here. And so we'd say negative 483.6 kilojoules is 1 mole here, and that's going to cancel out moles reaction. And now it's just a matter of doing the math, is going ahead and multiplying this out. And so 14 times negative 43.6 divided by 2.02 divided by 2. So when you do that, you end up with negative 1675.842 kilojoules. Now, a couple things that we need to look at here. Number one is sig figs. Now, we start off with 14 grams, only 2 sig figs. We didn't use anything else except for this, our delta H naught. And so for that one right there, for that heat of reaction, that has 4 sig figs. So since we're just doing multiplying, dividing, it should be 2 sig figs for our answer. And so we would normally get negative 1700 kilojoules. Now, the question is this released or is it absorbed? So question, which one is it? And so because of the fact that our answer came out negative, we know that this is going to be a loss of energy. It's going to be an exothermic reaction. It is not going to pull that energy in. It is going to release it. It is not going to absorb it. And so we would technically, in terms of saying this, just say our answer is going to be 1700 kilojoules are going to be released by the reaction. And so if we had to sort of write that up as our final answer, 1700 kilojoules released by the reaction, as opposed to 1700 absorbed, which it would have been if we came up with a positive number for our answer. So new example. This time we have a reaction between hydrogen gas and iodine gas to produce hydrogen iodide. In this case, our delta H naught is 52.8 kilojoules per mole. And so our question is this: how much heat is released or absorbed by reacting 8.8 grams of hydrogen gas with 5.9 grams of iodine at 25 degrees Celsius? So in this particular case, we don't know which one to start with. We've got to find the limiting reagent. And so limiting reagent works the same way as we did before. So let's just start with the hydrogen, 8.8 grams, this would be grams right there, of H2. And then we want to go from grams of hydrogen to moles of hydrogen. And so we'd say 1 mole hydrogen is just as we did before, 2.02 grams right here. That's going to cancel grams of hydrogen. We want to then go from moles of hydrogen gas H2 into what we're looking for, which is moles of iodine right here. And so we look at the prefixes or the coefficients, both 1. So 1 mole iodine to 1 mole hydrogen. That makes that easy. And then last step is we want to go from moles of I2 to grams of I2. So we have to look that up on the periodic table, and it ends up being, let's see, multiplied by 253.8. So 253, if we can fit it in here, 0.8. And so now it's just a matter of doing the math here. And this is definitely going to be a very large number. It ends up being 1,105 grams of iodine. And so of I2. And so do we have, so to use up 8.8 grams of hydrogen gas, we need over a kilogram of iodine. Do we have over a kilogram? No, it's 5.9 grams. And so as a result, we're definitely going to run out of iodine first. Iodine's our limiting reagent. And so we do have to find our limiting reagent on doing these reactions, same as we would in any other stoich problem. So we're going to start with that 5.9 grams of iodine. And we're going to try to convert it to find the amount of heat either released or the amount of heat absorbed in this particular reaction. And so we want to get rid of grams of iodine. We want to go to moles of I2. And so that's the same as it was before, 253.8. 253.8 grams in 1 mole, and so that cancels out grams of iodine. Now we want to go from moles of iodine, since we're looking for this mole that's right here, which is moles of reaction. We want to go to moles of reaction right here, and so the coefficient is 1 for iodine, so 1 mole iodine, 1 mole reaction, cancels moles of iodine. So now we want to go from moles reaction to kilojoules. And so what we know is 52.8. And I didn't buy myself much space here. I'm going to erase that really quickly. So we'd say 52.8, and that is positive kilojoules per 1 mole reaction. And so now it's just a matter of multiplying across the top. So 5.9 times 52.8 divided by 253.8 divided by 1 equals out to be unrounded 1.22 kilojoules. So we get. Now, in this case, this is a positive number, so that means their 1.22 kilojoules are flowing into the substance, which means they're going to be absorbed. And so sig fig-wise, we started with the 5.9 for this one right here, and so that means should be 2 sig figs, nothing else, because this has 3 right over there. So with 2 sig figs, our final answer is going to be 1.2 kilojoules are going to be absorbed by the reaction, which would indicate that the surrounding should be getting cooler, because a positive number here indicates that this is going to be an endothermic reaction. Next situation, 2C2H6 plus 7O2 yields 4CO2 plus 6H2O, where our enthalpy of standard enthalpy of reaction or enthalpy change is going to be negative 1560 kilojoules per mole. So our situation is here. What mass of ethane, which is C2H6, would be needed to be burned, or would need, never mind, I can't write. What mass of ethane would need to be burned to produce 5,000 kilojoules of heat? So this is a situation where you say, hey, I need a certain amount of heat. I need to heat my home or something like that, or I'm trying to cook a piece of meat or something, and I know I need 5,000 kilojoules in order to do that, and I want to burn some ethane in order to produce this. How much do I need to burn? So this would be a common question that we might be able to use. So for this particular situation, what we're going to do is we're going to start off with the energy, and we're going to go backwards and convert and find the mass. So first thing, let's look at this. It says we are producing 5,000 kilojoules of heat. That is, if it's being produced, then it's flowing out of the reaction, and so it's flowing out of the reaction. As far as we're concerned, we are going to start not with 5,000, but with negative 5,000 kilojoules, because of the fact that it is being produced, it is flowing out of the reaction, which means that from the reaction's perspective, it's losing 5,000 kilojoules. So always watch out about that. Just because it doesn't have a plus or a minus in the particular in the problem doesn't mean it's going to be always positive. You have to sort of read through it and see what it says to indicate that. Now, there's another quick indicator that sort of tells you that this is going to be a negative off of that, and that's if you look at delta H naught. You can see it's negative, and so since it's negative, we know it's an exothermic reaction, and if it's exothermic reaction, it's going to be losing heat, and so that means the reaction will be losing the 5,000 kilojoules. If you don't flip the signs around like this, if you left this as a positive, you'd end up getting a negative mass of your ethane when we get to the end here, and that's definitely not what you would expect to get. So let's just go ahead and set this up. So we have 5,000 kilojoules. First thing we want to do is that we want to get to our moles of reaction, and so we're going to put kilojoules on bottom. We're going to say moles of reaction on top, and so for kilojoules we're going to use our delta H naught, and so negative 1560 kilojoules per 1 mole of reaction. That's going to cancel out our kilojoules, takes us to moles reaction. And so now we're going to say moles reaction. We are looking to figure out the mass of ethane, C2H6. So we want to go to moles of ethane, C2H6 right here. And so 1 mole reaction is how many ethanes? There's a 2 is the coefficient, so it's going to be 2 moles ethane. That cancels moles of reaction, takes us to moles ethane. It asks for mass of ethane. And so we want to go from moles of C2H6 to grams of C2H6, and if we look that up, let's see, that is 2 times 12.01 plus 6.06. We multiply 6 times hydrogens right there, so it's being 30.08. If I'm doing the math right, 30.08 right here, and so that cancels out moles of C2H6. So now we just have to do the math. So negative 5,000 times 1 times 2 times 30.08 divided by negative 1560 divided by 1 divided by 1. Notice the negative signs cancel each other out, so we should have a positive answer for this. And when we multiply this out, I get 192.8 0.82 grams C2H6. And so sig fig wise, what do we start with? We started with 5,000 kilojoules. Well, that's around to the nearest thousand. That's the ones. That's I got only one significant figure. The 1560 has 3 sig figs. So we'll go with the 5,000 here as having just one. And so that's going to make our answer should have 1 sig fig. So it's going to be 200 grams of C2H6 for our final answer of the amount of ethane we need to burn to produce 5,000 kilojoules of heat. Some final notes. Because of the fact that the value of delta H naught depends on the number of moles in a reaction, we can manipulate the reaction equation to change delta H. So, for example, let's take this this hydrogen plus oxygen as water, this combustion reaction. So we said that the standard enthalpy change for this reaction is negative 43.6 kilojoules per mole. But that's with these particular coefficients, with a 2 and with a 1 and with a 2 out here. Now, that's the most reduced form. So if we just give you a delta H naught, then assume it's in its balanced most reduced form for this particular reaction. But if we were to change that, what if we doubled everything? Instead of 2 and 1 and 2 for this, we did 4H2 plus 2O2 yields 4H2O. It's balanced, but it's not reduced. And so this would not be our normal best way of doing this. But let's say that we did. In that case, because we doubled the values in the reaction, we're also going to have to double delta H naught. And so that means instead of being 43.6, we do negative 43.6 times 2, negative 967.2 kilojoules per mole. Second thing that comes up, sometimes you have to reverse a reaction. Now, if a reaction would be releasing heat, then reversing the reaction would have to be absorbing heat. In the case of this one, going from left to right, if we flipped it and went from right to left, then it would be endothermic. And it would be endothermic by the same amount of energy that it was exothermic before. And so if you're to reverse any reaction, flipping the position of the products and the reactants, the reaction would switch from exo to endothermic, and it would change the sign on your delta H naught. And so originally, if we're doing 2H2 plus O2 is 2H2O, we have a delta H naught of negative 43.6, but if we flipped it around, 2H2O yields, breaks up into 2H2 plus O2, now delta H is positive 43.6. And so that's something to look out for a little bit because there's a couple extra notes that you need to know about how these work.